Let us start this lecture with a thought process, that is, for leading a materialistic modern life, we burn fossil fuels like oil, gas, coal, etc., and produces billions tons of extra carbon dioxide each year that traps more of the sun's energy as heat, leading to global warming. We are all now experiencing the global warming, right, and burnt up it. So we need to also learn combustion in such a way that will minimize the carbon dioxide emission. Of course you cannot really, because you will have to use less fuel. That is the thing. That means if you make the process more efficient, so you will have to use less fuel, and also you will have to be a little bit miserly in using the modern gaskets, so that you can really reduce this global warming. So in the last lecture, if you look at, that is, we consider about the mass diffusivity, conductivity, and the viscosity properties of the mixtures and also the individual species. And today what we will be looking at, we will be looking at how we will take care of transport of mass in a bulk flow, right. There we are looking at individual microscopic effects, looking at, and then we connected those microscopic properties into the macroscopic properties like viscosity and conductivity and diffusivity. But here we will be looking at bulk, that means those properties we will be using here now, and which of course you will be knowing. Let us consider the mass conservation equation. That means mass has to be conserved in a fluid flow. Keep in mind that we are here considering what you call the continuum hypothesis, right. We are not considering that as if it is a discrete particles, it is all coming together, right. Right. So therefore because therefore we are not considering each individual particle now, it is a continuous. So the function will be also continuous in nature, and we will be considering a control volume approach, and let us say that we are considering a very small infinitesimally control volume. This is my control volume, right, and which is having a phase A, right, and this distance is basically delta y, and this distance in the phase B, and this is phase C, and this is basically delta x, this portion, this distance to this distance, and this is of course the D is again like coordinate. If you look at this point, delta x, delta y, this is the, and we are considering two dimensional in nature, but the z direction will be perpendicular to this plane, right, x and y plane. Now if you consider the, let us say, mass is entering to the phase A and leaving along the x direction through the phase B, right, and similarly some mass flux rho v y is entering through the phase C and it is leaving with the phase D. Now we want to look at basically the mass conservation. That means we will have to apply the principle of, right, by applying principle of mass conservation, right. We can have what is happening here in this control volume. We will have to look at rate of mass accumulation in control volume, that is rate of mass accumulation, right, in CV is equal to, what is that, whatever the mass is being accumulated here, which will be equal to mass in and mass out, right. That means rate of mass into CV minus rate of mass out, right, out of CV, right. Now, what is the rate of mass of accumulation in CV? That means mass, right. What will be rate of mass accumulation in CV? What it would be? Rate of mass accumulation in CV will be rho by dou T into volume, right. That what will be volume? Volume will be delta x into delta y. Of course, 1 we are taking perpendicular to this, I mean that is a 1. So, you need not take, that is basically volume, right. Unit depth we are taking, therefore, it is volume, okay, fine. And rate of accumulation of this in CV, you know. Now, we will have to find out rate of mass into CV. What will be? That means, I will have to, instead of this, I can say rate of mass entering into CV, right, through phase A, how much? That is be rho Vx into delta y, yes or no? Rate of mass CV through the phase is basically rho Vx into delta y, of course, into 1 you can say, right, right. And if you look at how much that at the phase B, what it will be? This is the flux change, how it is coming, how it is, because by Taylor series the flux, the mass flux, right, this is basically mass flux at phase B would be what? That is rho Vx plus d rho Vx dx into delta x. The rate of mass from CV through phase B is what? Rho Vx plus Vx by dx delta x into delta y into 1, isn't it, right. So, what will be the net flux in x direction? Net flux will be rho dvx by dx delta x into delta y, yes or no, right. Similarly, net flux in y direction Vy into delta x into delta y, yes or no. So, now if I put this is in equation 1 and this I can say equation 2 and this is equation 3 and equation 4, by using equation 1, 2 and 3, 4 or using equation 2, 3, 4 in 1, I can get 2 to 4 in equation 1, we can get as basically d rho by dt, right, is equal to Vx by dx minus this will be actually this will be fx will be in direction will be basically minus this, right. This will be minus this minus rho v y by dy. So, similarly I can write down d rho by dt plus d rho vx by dx plus d by dou y rho vy is equal to 0. So, now that will be rho vx dx by rho vy dy. If I this is 5. So, if you look at basically I can write down in a vector notation as equation 5 can be rewritten in vector notation as d rho by dt plus delta dot rho v is equal to 0. So, if you look at delta dot rho v is nothing but your divergence of rho v, and what does it indicates? If you look at this indicates the rate of gain of mass or accumulation of mass per unit volume. And this is of course the mass flux, which one? Rho v, and this term is basically net rate of mass flow rate per unit volume. I think net rate of mass flow per unit volume. And for a steady flow, if you look at we can write down, right, equation 5 becomes rho vx dx plus rho vy dou y is equal to 0. So, keep in mind that in our course we will be mostly dealing with one dimensional flow, but in some situation we may go for 2 dimensional, right. We will definitely not going to the 3 dimensional flow because it is not tractable, particularly for combustion situation. So, if I consider for steady 1D flow, right, that equation 6 becomes rho vx by dx is equal to 0, implies that rho vx is constant. What does it mean? It means that if the density is decreasing, what will happen to Vx? Vx has to increase, and in combustion problem what will happen? There will be increase in temperature, particularly where the flame will be there. So, therefore, at that place what will happen to density will be decreasing, so the Vx will be increasing. So, therefore, one has to careful about it, and you cannot really make that flow to be incompressible, like, you know, are you getting? So, that you should keep in mind, because from this you know, it can well say that rho, if it is, you know, increasing, the Vx has to decrease and vice versa, right. For example, I am going from let us say high temperature to the low temperature, right. Then naturally what will have, density will increase and Vx has to decrease, right. Other around, if you are going from low temperature to the high temperature region, so this has to be what you call rho has to decrease, Vx has to increase. So, of course, this is for the Cartesian coordinate system, are you getting? Now, we will be also dealing with cylindrical, like for example, there is a jet flame, right. For that, in that case, Cartesian I can use, but that will be not that convenient. So, I will have to use cylindrical coordinate system, right. For the cylindrical coordinate system, if I look at here, right, let us say this is the Z and right. So, this is I am saying this is x, right, and this I can say this is your Z direction, right. But I am having here a point, right. If I say that is coming over somewhere here, that means this is my r, right, and this is my what you call theta, that is azimuthal angle, right, and this is my Z direction. So, right, this will be Z direction. So, if I will say this is my unit vector will be what you call that will be Z, right, this will be basically r direction, right, and this will be theta, or is it not visible here? So, this will be r unit vector. So, I can write down this, you know, continuity equation whatever we have derived for the Cartesian and coordinate system, right, for steady axisymmetric system. The continuity equation becomes one by r d by dr into r rho v r plus z into rho v z is equal to 0. And keep in mind that v theta is basically azimuthal direction, you can say this is basically 7. And similarly for spherical coordinate, right, for steady spherical system, right, the continuity equation right 1 by r square. I am writing now basically for the maybe what you call 2 dimensional, right, r and theta. So, dou by dou r square rho v r plus r sin theta into dou theta rho v theta sin theta is equal to 0. Keep in mind that if you compare this equation with the cylindrical system, what you can see, this is in place of r, in case of axisymmetric system it is r square is coming, right. Of course, this term is different, like the second term is different. Keep in mind that, like, if I will consider for one dimensional flow, right, because we will be using that for 1D spherical system, right. What it would be? It will be basically equation 8 becomes 1 by r square dou by dou r square rho v r is equal to 0. What is the meaning of that? Basically r square rho v r is constant, right. That means if you look at, this is nothing but your mass flow rate and r square is your area, right. You can say that this is nothing but your rho v r pi r square, right. I can write down this is nothing but equal to constant. In this case, of course, what is happening if you compare one dimensional flow in the coordinate system, like what you call Cartesian coordinate system, that is the area is not coming into picture. Here the density will be decreasing, that means V r also may increase, may not increase depending on the area, right. Are you getting? So, in the r direction, that means V r square also will be increasing. So, density is decreasing and V r square is increasing. Now, V r effect will be there, but that will be very less as compared to what you call Cartesian coordinate system. Like if it is a straight line, right, going, there is no effect of that sphere or the spherical, then that comes into picture. So, these things we will be using, particularly when you talk about what you call droplet combustion, then we will be using spherical coordinate system. When we will be talking about the jet flame, we will be talking about cylindrical coordinate system. When we are talking about one dimensional flame, we will be talking about Cartesian coordinate system. So, those things we will be discussing, and I think we will stop over now, and in the next lecture we will be discussing about the momentum equations, right, conservation equation. Thank you very much.